This video is part of the Membrane Versus series, and this one compares the membrane bioreactor, or MBR, and the Conventional Activated Sludge process, or CAS, focusing on just a few key parameters. Descriptions of both the Conventional Activated Sludge process with classical sedimentation used for cell recovery and the immersed MBR technology, which uses membrane separation, are provided in our other videos. There's also a video on the different MBR process configurations. In this video, though, we'll focus on the key differences between the MBR and the CAS. The key bases for comparison of these processes, and most others, are cost, purification performance, that's how much pollutant is removed, and emissions, including from waste. Costs are normally categorised as either capital or operating expenditure. CAPEX is made up of a number of components and is influenced by, amongst other things, the plant footprint. That's how much ground area it takes up. The primary contributors to OPEX are energy consumption, staffing requirements, and critical component replacement, most importantly, the membrane in the case of the MBR. Some of these are too complex to allow a rapid appraisal, but let's look at purification, footprint, and energy. With purification performance, it's fairly obvious that water which is being filtered through a 0.1 pore-sized membrane will have a lower turbidity and pathogen content than water which has only undergone settlement by secondary clarification. However, as well as this, because an MBR operates at longer solids retention times, which gives higher mixed liquor suspended solids concentrations than the CAS, the bioreactor levels of slow-growing active microorganisms like nitrifiers are higher in the MBR. This leads to slightly more efficient organic carbon and nutrient removal by the MBR compared with the CAS. Now, let's consider footprint. Since MBRs operate at higher MLSS concentrations, the number of active microorganisms are concentrated into a smaller volume than for a CAS. This means that the process tanks of an MBR can be made smaller than for a CAS. And the same is also true of the solids-liquid separation step. The flow per unit floor area through a CAS clarifier is given by the surface overflow rate, which relates directly to particle settling velocity. For membrane separation, the same parameter is given by the product of the packing density and the permeate flux. Because sedimentation is relatively slow, whereas the membrane packing density can be made quite high, the footprint of a membrane tank or skid is generally less than half that of the conventional clarifier. We'll look at this in more detail in a future video on membrane technology versus clarification. But next, energy. The main contribution to energy consumption is from blowing air. Since for an immersed MBR, air is used both for feeding the microorganisms in the process tank and scouring the membrane, the energy demanded is higher for an MBR than for a CAS, where only the process air is needed. This is exacerbated a little by the higher MLSS concentration in the MBR process tank, which constrains the mass transfer of oxygen from the air and so increases the aeration demand further. Finally, considering OPEX, the higher energy consumption and the requirement for membrane replacement every 6 to 10 years or so means that the OPEX for an MBR tends to be higher than that of a CAS process. However, because of the smaller tanks, the MBR civil engineering costs tend to be a little lower than for a CAS of equivalent flow capacity, even after buying the membrane. So there you have it. A very brief summary of just a few of the differences between the MBR and the CAS processes. There are, of course, many others.